Calculate the pH of a solution that contains 1.2 moles per liter of hydrogen cyanide or hydrocyanic acid, whose Ka is 6.2 times 10 to the negative 10, very, very weak, and 4.0 molar HNO2, hydrogen nitrite or nitrous acid, whose Ka is equal to 4.0 times 10 to the negative 4. Also, calculate the concentration of the cyanide ion at equilibrium. Okay, so we want to find the pH. So we have a mixture. We have this certain amount of water. We drop in some 4 molar hydrogen nitrite or nitrous acid. We drop in 1.2 molar hydrocyanic acid. We want to know what the pH of the solution is, and we want to know what the concentration of the free cyanide ion is in that solution. Okay, let's list our major species with their particular equilibriums. Well, so let me go back to blue here. So major species in water. That's what we're doing. We always want to do the major species to decide what chemistry is going to dominate. Well, HCN is a weak acid. That means it's mostly HCN. It hasn't dissociated. Strong acid dissociates. Weak acids, not very much. We also have HNO2 floating around in that. And we have H2O. Well, the HCN equilibrium, H plus plus Cn minus, we said the Ka is equal to 6.2 times 10 to the negative 10. Oops, wow, look at that. That's a crazy line. Okay. And then the HNO2 equilibrium, NO2 minus, the Ka for this one is equal to 4.0 times 10 to the negative 4. And of course we have the, here we go again. Wow. And last but not least, we have the H2O equilibrium, which is also another source of hydrogen ion, plus OH minus. The Kw equals 1.0 times 10 to the negative 14. So now let's compare. 10 to the negative 10, 10 to the negative 4, 10 to the negative 14. We can virtually ignore the 10 to the negative 14. It's too tiny. Between 10 to the negative 4 and 10 to the negative 10, this one, the HNO2, this is going to dominate the chemistry in this solution. Because that's going to dominate, we can ignore any contribution of hydrogen ion from cyanide, from hydrogen cyanide, and we can ignore any contribution of H plus from water. And again, we're doing this because there are 3 sources of hydrogen ion. Some can come from HCN, some can come from HNO2, some can come from H2O. But the Ka of the HCN and the H2O are so tiny that they're negligible. So this is what controls the chemistry of the solution. That's the chemistry we concentrate on. Therefore, let's go with HNO2, H plus, plus NO2 minus. Now, you're going to do the same thing that you did before. You're going to make a little ice chart. Initial, change, equilibrium. You're going to do your simplification. You're going to check it. Everything is going to be fine. You're going to end up with a pH of, I hope you actually go ahead and run through and do this based on the previous 2 examples. So for this one, you're going to end up with a pH of 1.40. Now the question is, the second part, how do we find the cyanide ion concentration? Okay, let's write down the cyanide equilibrium. We need to find the cyanide ion concentration, so we need to work with the cyanide equilibrium. HCN goes to H plus plus Cn minus. Ka equals 6.2 times 10 to the negative 10. Now let's stop and think about what this means. This is saying that in a given solution where you have cyanide ion, hydrogen ion, and HCN and hydrogen cyanide floating around in solution, these three species floating around in some concentration each, the equilibrium concentration, in other words, the concentration of this times the concentration of that divided by the concentration of this equals 6.2 times 10 to the negative 10. Remember, that's what an equilibrium expression is. Equilibrium positions can change, but the constant stays the same. The relationship among these three, that's what equals this. It doesn't matter where these H plus come from. This is talking about, at any given moment, if you have cyanide, hydrogen ion, and hydrocyanic acid in solution, the concentration of this times that divided by the concentration of this always equals that. So this gives us a way to find it. It doesn't matter where these H plus come from. They can come from HCN or they can come from any other source. Any other source. In this case, the primary source of the hydrogen ion is the nitrous acid. It is the dominant species in the water. It's the one that's going to give up its hydrogen ion, suppress the others. So at equilibrium, there is a certain concentration of hydrogen ion, and that concentration of hydrogen ion was the 1.4 that, well, pH was 1.4. The 1.4 came from the negative log of the hydrogen ion concentration. So now let's go ahead and work this out. This says, so we know that the Ka is equal to H plus concentration times Cn minus concentration over HCN concentration. That equals 6.2 times 10 to the negative 8. This is the equilibrium expression. Well, let's see. Let's go ahead. So at equilibrium, we have, no, not 6.2 times negative 8, we have 6.2 times negative 10. Yeah, that's 10. So that means 6.2 times 10 to the negative 10. Now we go back on our ice chart and we read off this, this, and this. We ended up with our equilibrium concentration is 0.04. That was the hydrogen ion concentration that gave us the pH of 1.4. We have the Cn minus concentration, and at equilibrium, the HCN concentration was 1.2 minus X. Okay. Again, we're just dealing with a basic math problem, but as it turns out, we have a little bit of a problem. We have this X here, smaller than normal, would suppresses the HCN dissociation. Let's see here. Let me see, how do I want to go ahead and explain this to make it most reasonable? We have that, we have that, we have the cyanide concentration. Okay, let me erase something here. Okay, so let me rewrite this here. HCN, H plus Cn minus. Now, at equilibrium, we started off with 1.2 molar of the 1.2 molar of the HCN, right? So this was 1.2 molar. Now we have the H plus concentration, which is 0.04. This is the equilibrium concentration. This is what we want, this Cn minus concentration. Now, it's true that of the HCN, some of it will dissociate. So the fact of the matter is, the equilibrium concentration is going to be 1.2 minus X. But again, remember what we said, the dominant equilibrium here was the nitrous acid. And it's so dominant that it's actually going to suppress this dissociation. Anything that HCN would actually produce, any H plus, is virtually non-existent, because not only was it small to begin with, but because there's so much of the H plus from the nitrous acid, it's actually going to push this even more that way. So there's going to be even less. So for all practical purposes, we don't even have to worry about any HCN dissociating. Therefore, our final equilibrium will end up actually being 6.2 times 10 to the negative 10 is equal to 0.04, which was the hydrogen ion concentration we found from the HNO2 dissociation, times the CN minus concentration over the HCN concentration, which was 1.2 molar. And then when we solve for this, we end up getting a CN minus concentration, and this time I will use the square brackets, 1.86 times 10 to the negative 8 molar. So as you can see, 1.86 times 10 to the negative 8 molar is so tiny. That means there's virtually no cyanide ion floating around. And that is based on this equilibrium. So again, if you have a mixture of acids, one of those acids will dominate the equilibrium. If you're asked for the concentration of a species from the other acid, the one that's not dominant, you can still you just write out its equilibrium, and it just means that in this particular case we wanted cyanide. Well, the equilibrium expression for HCN says that cyanide concentration times H plus divided by this equals this. Well, we have this from what we just calculated from the dominant species. We have this, which is the original concentration. And then all we have to do is solve for this, because we already have this. 1, 2, 3, 4. We have 1, 2, 3 of them. We solve for the fourth. There you go. I hope that made sense. Okay. Let's see. So we've taken a look at some weak acid problems. We have listed the major species. We take a look at the major species to decide which one is dominant, and usually in this particular case for weak acids, we just see which one has the higher Ka value. Whichever one has the higher Ka value, that equilibrium, that acid will dominate the chemistry of the solution. We write its equation. We list its initial concentration, the change in the concentration, the equilibrium concentration, and then we put the equilibrium concentrations in terms of X into the equilibrium expression, and we solve for X. And more often than not, they're going to ask for calculating the hydrogen ion concentration, or more accurately, the pH. More often than not, they'll just straight out ask for the pH. So thank you for joining us here at Educator.com and AP Chemistry for weak acids.